In the previous video, we discussed about graphs of functions, and also we added, multiplied, subtracted and divided to real valued functions. So today we are going to see a few more things. So the first one of them is composition of functions or composite functions. So the definition goes like this: if f and g are functions, then the composite function denoted like this and is read like this: f circle g is defined as this. Okay, so this is the definition of this new function, which has been defined using the functions f and g. The domain of f circle g consists of those numbers x in the domain of g for which the number gx lies in the domain of f. Because you see, then only this expression f of g of x makes sense. First of all, x should come from the domain of g. That is the first thing, so that g of x makes sense. And then, in order to calculate f at g of x should lie in the domain of f. It may not be the case that for every x in the domain of g of x lies in the domain of f. That may only be a subset of the domain of g. But we can take only those x's only. So the natural domain of f circle g will consist of, say this is the domain of g. Okay. dg. Now we are choosing x from here, and x gets mapped onto gx. Some x prime also we choose in the domain of g, which gets mapped onto gx prime. It may happen that the domain of f contains gx prime but does not contain gx. Then f of g of x will be meaningless, because this does not make sense. This makes sense only when the thing inside f, the argument of f, lies in the domain of f. But this makes sense. Okay, so the natural domain of f circle G should consist of numbers like x prime, not like x. Okay, so that's why we say the domain of f circle G consists of those numbers, although we have written, actually we should have written x prime here, so that say this is so this is x prime and this is x. Okay, so that this is not defined, so we want those type of numbers x in the domain of G for which G of x lies in the domain of f. There may be some points in the domain which are not reached by the function G, that is fine, but whatever points are reached by G, we can only consider the corresponding inputs here in the domain of G. That will determine what the domain of f circle G is. So the definition says from this little diagram you can see that there is one case where you cannot define f circle G at all. That case arises when the domain of G is such that any point of G, any point in the domain of G gets mapped by G onto a number that does not lie in the domain of f. That is, the range of G and the domain of f are disjoint, they have no point in common. Then f circle G cannot be defined. So that's why this next paragraph says, the definition says that two functions can be composed if the range of the first contains the not contains is contained in the domain of the second. Range of the first, or in other words, it lies in the domain of the second. If we are thinking of the two functions as f and g, then in this context, in the context of forming f circle G, which is also we say it like f composition G. In this context, the first function that we are calling here is G, not f. Okay, not in the order in which they appear. The first one in this context is G, because that is the one which we apply to x first, and then on the result we apply f. F comes afterwards. The first function, the range of the first function, they are saying should lie inside the domain of the second. Now this is actually a special case of this. If this happens, then the natural domain of f circle G the composition function need not be a restricted subset of the domain of G. It will be the entire domain of G, because now every G of x lies in the domain of F. So for every x in D of G, you can form F of G of x. So there is no problem with any x in the domain of G, and the domain of F circle G is equal to the domain of G. That is the biggest domain possible, and that can be taken. This does not exactly match with this. There is a little discrepancy. This one, what they are saying, what the authors are saying here, is a special case of this one. Ideally, they should have said this, that F composition G can be formed when the range of G, this is the range of G, this set, and the domain of F has non-empty intersection, so that there are some points which get mapped onto that common area or the intersection, and for those points they make up the domain of F's composition G or F circle G. But anyway, they have considered a special case of this general situation. I hope these things are clear. It will be somewhat difficult to understand in the beginning, but the more you think about these things, the clearer they will become. And in the scheme of this entire thing, to find F circle G of x, yes, we first find G of x and then F of G of x. That is the order in which things have to be calculated. Because F is appearing first, that does not mean F has to be applied first. You have to start the application on x of the function that is closest to x. That's why x has been written here, and that's why the notation looks like this. F composition G, you have to apply G first, and then on that you have to apply F. And there is a diagram which is actually this thing itself that appears after this. In that diagram, we just have a sort of irregular region. This is the place from where x is coming. And x gets mapped onto G of x by G, and then G of x gets mapped onto F of G of x by F. So this is F, this is G. When this happens, then according to the definition of our new function F circle G, that maps x onto this element. Okay, so that is composition of F and G. Now, just like you can form F composition G, you can think of G composition F also, provided the conditions that we were laying out here in the definition of F composition G is true for G composition F. That is, in short, provided G composition F can be defined. So next, to evaluate the composite function G composition F when defined, the situation may not permit you to define G composition F. Maybe the domains, range, all the things of F and G are such that you can only form F composition G and G composition F does not make sense. That may be the case, but when it is defined, we reverse the order naturally. We reverse the order, finding Fx first and then G of F of x. So just like that other function, the first one, the domain of G circle F consists of those numbers x in the domain of F for which F of x lies in the domain of G. Here the roles of F and G have been swapped, have been interchanged. In general, the functions, when both of them are defined, F composition G and G composition F are usually quite different. Now there is an example to illustrate these concepts. This is example 6. If f of x is the square root of x and g of x is x plus 1, then find let me refill. Then we have to find four compositions which are these: F composition G of X, G composition F of X, C, F composition F of X, one can think of that also, and D, G composition G of X. And in each case we will find the natural domain of the composition. In the text it's given as a table, so we will also do that. The composite function they appear in this column, and their respective domains appear here in the second column. Okay, so first we have F composition G of X. So this is F of G of X, and that is equal to, because of lack of space I have to write in a new line. G of X is X plus 1, and F of X plus 1 is square root of X plus 1. Now the natural domain of this function is the set of those x's for which X plus 1 is a non-negative real number, that is, for which X plus 1 is greater than or equal to 0. In other words, it's the set of those real numbers x which are greater than or equal to minus 1. So the natural domain in this case is this ray, closed ray, minus 1 comma infinity. B, G composition F of X. So this is G of F of X. So G of square root of X, that means this is root X plus 1. Now this one is even easier than this. X just has to be non-negative, that's all. So the natural domain in this second case is the set of all non-negative real numbers. Then in part C we have F composition F of X. So this is F of square root of X, which again is the square root of the square root of X, that is X to the power the 1 by 4, the fourth root of X. Here also, just like the square root, the second case, the natural domain is the set of all non-negative real numbers, because this is in this case also you cannot take negative real numbers, everything else you can take. And finally in part D we have this. So this is G of X plus 1, which again is X plus 1 plus 1, that is X plus 2. Now here we don't have any restriction at all, you can take all the real numbers. So here the natural domain is the entire set of real numbers, or if you want to write an interval you can write this. So that is all the compositions. The next concept is even functions and odd functions. And how they are related to the concept of symmetry. A function y equal to f of x is called an even function if f of minus x is equal to f of x for all x in the domain of the function. For all numbers x in the domain of f. Okay, from this definition you can see one thing, apart from of course this condition that evenness of a function requires, besides this or you can say what I am now going to say is a part of this condition that defines evenness, that for any x in the domain of f, minus x also lies in the domain of f. That kind of domain f should have. First of all, that is the first condition, and the second condition is that at x and minus x the functional values must be the same. Note that for a or for an even function we can directly write like that. F both x and minus x belongs to the domain of f for every number x in the domain of f. If you encounter a function for which there is one number x in its domain for which the negative of the number does not belong to the domain, then there is no point verifying this equation, because this part of the equation will not make sense for that x. So this condition first of all should be true. Since now next we come to the question of symmetry. What does this definition have to do with symmetry? Since f of minus x is equal to f of x, the point x comma y lies on the graph of y is equal to fx if and only if the point minus x comma y also lies on the graph. Thus, the graph of an even function is symmetric about the y-axis. If we know the graph on one side of the y-axis, then we also know it on the other side. So because f of x and f of minus x are the same, so any point x comma y that lies on the graph of an even function y equal to fx has a corresponding point minus x comma y also lying on the graph. And because of this, geometrically the graph is symmetric about the y-axis. In the sense that if you think of the y-axis as a mirror, then one part of the graph which lies on one side of the y-axis will be the mirror image of the other part lying on the other side of the y-axis. So in that sense, if you know the graph on one side of the y-axis, you automatically know it on the other side. To illustrate this, we take the example of the square function, which is an even function. The function y equal to x square is even because minus x whole square is equal to x square for all x belonging to the set of real numbers, which is the natural domain of the square function. Geometrically, the consequence of all these things is this. If I draw the graph of the square function, which I am going to do, see, already I messed up. Okay, it looks roughly like this, a parabola. This is the y-axis, this is the origin O, this is the x-axis, and this is the graph of y equal to x square. Because this is an even function, on this side the graph looks like this, and this is just the mirror image of that. For any x you have here, you have the point x comma y here, where y is nothing but x square. On the other side, if you consider minus x, then you have the other point here. minus x comma y, where minus x is, minus x whole square is also equal to y because it is x square, and these two lie on the same horizontal level. That is because the y coordinates of these points are the same, and this is true for any x minus x pair. Okay, so this is the symmetry of the graph about the y-axis, and this comes from the evenness of the square function. Just like that, we have the notion of an odd function. A function y equal to f of x is called odd if f of minus x is equal to, this time it is minus f of x. For every number x in the domain of f. Just like before, for an odd function, both the numbers x and minus x should belong to the domain of f for every x in the domain of f. And just like the even function case, here also there is a kind of symmetry to the graph of an odd function. Since f of minus x is equal to minus f of x, the point x comma y lies on the graph of the odd function y equal to f of x if and only if the point minus x comma minus y lies on the graph. So in this case, the symmetry is not about the y-axis, but the symmetry is about the point origin itself. Thus, the graph of an odd function is symmetric about the origin. If we know the graph, on one side of the origin, then we also know it from the symmetry on the other side. And this time we are now going to consider the cube function, which is an odd function. The function y equal to x cube is an odd function. Because minus x whole cube is equal to minus x cube for all real numbers x. And if one draws the graph of the cube function, okay, this will be even more difficult for me to draw than the square one, because the graph is wavy. You already know how the graph of the cube function looks. We have shown it in the list of graphs that we presented in the previous video. It is somewhat like this, and if this is a point x comma y, this is the graph of y equal to x cube. X, this is the origin, this is the y-axis. Then the point minus x comma minus y also lies on the graph, and conversely. So if you know this part, one side of the origin you know, then you also know the other part. That kind of symmetry. So that is the symmetry of an odd function. So these are the notions of even functions and odd functions. Next, piecewise defined functions. Sometimes a function is defined by different formulas on different parts of its domain. Such functions are called piecewise defined functions because on different parts of its domain it has been defined using different formulas. So in separate pieces, the entire formula of the function comes. For example, we have already come across one such function, which is the absolute value function. One example is the absolute value function, which is defined like this. We know that the absolute value function has the entire set of real numbers as its domain, because for every real number we can find its absolute value, and the function itself is defined like this. It is defined to be x if x is a non-negative real number, and is defined to be minus x if x is a negative real number. So on the non-negative part of the domain, the formula is x, and on the negative part of the domain, the formula is minus x. Two different formulas. So it's a piecewise defined function, and its graph, I don't remember if we have seen the graph of this function before, but you can clearly draw the graph. This is y, this is x, this is the origin. You just have to observe that on the non-negative side, the equation of the function is y equal to x. So on that side, the graph will look like this. The equation of the line y equal to x, but only for non-negative values of x, and on the negative side the equation is y equal to minus x. So on that side the slope of the line is minus 1, so it will be this line. So this is the graph. These lines, of course, they go on without any end. This is the graph of the absolute value function y equal to absolute value of x. So this is one example of a piecewise defined function. There are other examples also. And some such examples are given next. Example 7. Consider the following function. F of x is defined to be equal to minus x if x is negative, then x square if x is non-negative but less than or equal to 1 and is equal to 1 if x is greater than 1. It is a piecewise defined function. Piecewise defined functions we will use when we study integration. Okay, much later in the book when we study integration, piecewise functions will be important because they are in fact precisely piecewise continuous functions. We will see those things. Let us draw its graph. It's enough to just see the general shape of the graph. Because of the different formulas, the graph will look different in those parts. The part on the negative side of the x-axis is, you already know, it will be just this, because there the formula is same. Here also it is minus x, here also it is minus x when x is less than 0. So on this side the graph, this is the graph. Okay. Then choosing some unit length, between 0 and 1 the function is just the square function. So there you have the part of the parabola, somewhat like this. And then after 1 the function is constantly 1. So this is how the entire graph looks. So this is another example, and then so in fact looking at the graph also sometimes you can see that parts of that it is a piecewise defined function, and here the formula is minus x. From the graph itself you can guess that here the formula is x square and here the formula is constantly 1, because the height does not, y value does not change. The next 2 more examples will be given. This one has a name. The greatest integer function. The function whose value at the number x is the greatest integer less than or equal to x is called the greatest integer function or the integer floor function. The definition at once will be somewhat difficult to understand, but the examples will help us. It is denoted as this. That is the functional value at the real number x, or in some books as this. Or there is another notation which I haven't seen anywhere actually other than in this book, I mean particularly here. We will use throughout we will use this notation. Note that okay, so some examples are given. The functional value of this function at the real number 2.4. Okay, let us now take time to see what the definition is. At the real number x, the value of this function is the greatest integer less than or equal to x. Now, there are many integers less than or actually none of them is equal to 2.4 because 2.4 itself is not an integer, but there are many integers less than 2.4. In fact, infinitely many integers. All of these integers, -4, -3, -2, -1, 0, 1, 2, and the other integers are not less than 2.4, they are greater than 2.4. Among all these integers that are less than 2.4, the greatest integer is 2. So that is the greatest integer less than 2.4. Less than or equal to 2.4 of course, but the equality condition is not satisfied here. So this is equal to 2. To determine the value of this function at some number, you think of the number on the real line, and then to the left of the number you look at all the integers. The closest integer is the value. Like that, the greatest integer value of 1.9 is 1. Okay. The greatest integer value of 0 is 0 itself, because the integers less than or equal to 0 are all the negative integers and 0, because 0 now is included, and among them the greatest is 0. So this is 0. Then let us take a negative x value. These three examples may give you a sort of false formula for quickly determining the value. You may notice that you just have to ignore the decimal part, I mean the fractional part of these numbers, the inputs. And for example, here you have 2.4, you get 2, forgetting about 0.4. Here 1.9, you have 1. Here you don't have any fractional part, so you have 0. But don't make such simple rules just from these three observations, because that is wrong. This value is not -1. Think of the situation. what are the integers less than minus 1.2? There are many. Minus 1 is not less than minus 1.2. Minus 1 is greater than minus 1.2. Minus 1 lies on this side. So among these integers less than minus 1.2, the greatest is minus 2. So instead of getting minus 1 here, you are actually getting minus 2. So be careful to formulate such rules. Already the definition is somewhat confusing in the beginning, so it's better to use the definition always. So this is minus 2. In fact, I would suggest you not make such rules, okay, so that you can memorize those rules. This is one of the, not one of the, this is the worst way of learning mathematics. Creating tables, mugging up formulas, memorizing them without understanding how they came or from where they came. So that type of learning actually is not learning at all. It is just simply memorizing some information and then using them without really understanding how they are to be used, or in fact in some cases even what they mean. It's always better to understand the concept and then see what the things are that are following from the definition. This of course is 2, and then 0.2, this is 0. Sometimes such rules help us in writing exams, but in general I am always against memorizing things as far as possible. The integers less than, this is minus 0.3. The integers less than or equal to this real number are all the negative integers, okay, up to minus 1. Among them the greatest is minus 1, so this is minus 1. And some simple observations show you that if your x itself is an integer, then the greatest integer function value is x itself. Okay, that thing is true, but you should know why that is true. Now, what sort of graph can you have in this case, and why is it a piecewise defined function? Because in the definition we don't see it as a piecewise defined function, but the graph will tell you, once you draw the graph, that it is actually a piecewise defined function. Should I make the x-axis a little long? I don't think I need that. Okay, let us now carefully put some points. 1, 2, 3. Here also 1, 2, 3. One, 2, 3. Okay. Now we have to think of, these are only just some values. We need to know what happens in some intervals. For example, what happens in this interval 0, 1. If your x is lying here, that means x satisfies these inequalities. Now you have two cases. Either x is equal to 1 or x is less than 1. Say x is less than 1. Then where are the other integers that are less than x? They are here. So from here itself you can see that the integers less than or equal to x are these, all the non-positive integers. Among them the greatest is 0. So on this half open interval the functional value is 0. That means the greatest integer value is 0. So at 0 it is 0, and until we get to 1 it stays 0. At 1 it is not 0. At 1 the value is 1. So there is a sudden jump. So this is the graph. This line segment does not reach the point x equal to 1. It just does not reach the point. At 1 it is equal to 1. Okay, now what happens in this interval, that is in this half open interval? So this is our 1, this is 2, this is 3. Here the integers less than x, or less than or equal to x I should say, are all the non-positive integers and 1. That is all these integers, all the negative integers and 0 and 1. Among them the greatest one is 1. So in this interval the value is constantly 1. So until you reach this point, this is the graph. Like that, from our experience gained in these two half open intervals, we can then quickly determine what the value will be in this interval. It will be constantly 2. One, 2. So this point is not a part of the graph, just that point, okay, not anything else. So this is you can see that the graph appears in broken parts. What happens on the negative side of the x-axis? For example, on this interval, actually nothing significantly different than what we are having here happens on that side. Here the inequalities that x satisfies are these. So for such an x, the integers less than or equal to x are all negative integers. Among them, the greatest is -1. So in this interval, that is where you have 1 and you don't have 0, this is the graph, constantly -1. So you can now see the general pattern. If you go to higher values of x, you will have other steps like this, and if you go to the negative side, the steps will descend. So that is why it's also sometimes called step function. And see, integer floor function. So it goes like this on this side, goes like that on that side. Okay, so I hope you get the idea of why the graph looks like broken steps. It's the entire graph looks like a staircase. Okay, now comes the question of why it's the piecewise defined function. That is because instead of using the greatest integer and all those things, you can, if you want, define the function like this. The function is defined to be 0 if this, okay, it is defined to be 1 if x lies in this interval. It is defined to be 2 if x lies in this interval, and so on. And similarly for negative values of x, -2 if so that's how also one can define the function. But actually one, you can see, will get the same function. So that is why the greatest integer function or the floor function, integer floor function or the step function is a piecewise defined function. And you can now almost see that it has a cousin, this function, which is the least integer function. So that is the next thing. Example 9. The least integer function. The function, okay, that it starts like this, the language is this. The function whose value at the number x is the least integer greater than or equal to x is called the least integer function or the integer ceiling function. Like that is called the floor function. This is called the integer ceiling function. It's denoted as this. This is the floor and that is the ceiling. Okay, so we have the horizontal bars above on top of x. This function might represent for instance the cost of parking in a parking lot. For X hours in a parking lot that charges $1 for an hour. For each hour or part of an hour. So the graph of the ceiling function is just like the graph of the floor function, but it is somewhat different, a little different. Here also you will get steps. So, okay, I will not draw the graph. Instead, let us just find the functional values at some points, and based on how we drew the graph of the integer floor function, I leave it to you. You draw the graph of the ceiling function. Instead, let us calculate the ceiling values of precisely those numbers for which we found the floor values. What is this? So the definition of the function says that this is the least integer greater than or equal to 2.4. So to calculate the floor value, we looked to the left of 2.4. Now we have to look to the right of 2.4. We have to look at the integers that are greater than or equal to 2.4. No integer is equal to 2.4, of course, but the ones that are greater than 2.4 are these 3, 4, 5, etc. Among them, the least one is 3. So this is equal to 3. If you really want a quick way to find these values, either for the floor function or the ceiling function, you can, I won't say it's a formula, but it's a technique. You just think of the situation geometrically. You think of the point on the line. This is your point. To find the floor value, you look at the closest integer that lies to x. That is the floor value. And the closest integer that lies to the right of x is the ceiling value. If x is an integer, then these two values are equal to x. Otherwise, they are not. Okay, so what will this one be? This will be 2. Then for 0, of course this is 0 again, and then we had minus 1.2. This will be minus 1 because all the integers that lie to the right of x are minus 1, minus 2, see what the hell am I saying, minus 1, 0, 1, 2, 3, etc. Among them the least is minus 1 or the closest one is minus 1 to this number, so it is minus 1. Then this is equal to 2, 0.2, this is 1, minus 0.3, this is 0, and minus 2 of course is minus 2. Oh, sorry. The ceiling function is less frequently used than the floor, so I have got a habit of writing the floor. So it's the graph of the ceiling function is left to you. And that ends this section. After that, in the next video, we will start solving the exercises. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.